How you doing? Hope you're having a good day. Today I'm going to continue the series on stimulated Raman scattering, and we're going to discuss what the actual experiment looks like. So to actually do the experiment, you need two laser pulses. One of the laser pulses is called the pump pulse. And let's say the pump pulse has an electric field vector E1, and let's say that equals E1 naught times cosine K1 x minus omega 1 t. And we have a Stokes pulse. Let's call that E2, and that's equal to initial amplitude E2 naught times cosine K2x minus omega 2t. These are just the form of a general sinusoidal wave. And the difference between the frequencies, so omega 1 minus omega 2, is going to be our vibrational frequency of interest. So we start with the sample, we shoot E1 at it, and let's say E1 has n photons. We also shoot E2 at it. Let's say E2 has m photons coming in. What's going to happen is some interactions, and what you're going to get out is m plus 1 photons in the Stokes beam, and from the pump beam you're going to get n minus 1 photons. And notice how photons, they have to stay conserved, the number of photons. And since we gained a photon here, the process that's happening here is called stimulated Raman gain, which is abbreviated SRG. And since we lost a photon here from the pump beam, we call it stimulated Raman loss. So the first thing that happened is we started in a ground vibrational state. We can call it A. Next thing that happened was E1 came in, brought us to a virtual state. We'll call that virtual state state N. And this was E1. This was the real part, interacted with a real part of E1. Then we went down to a vibrationally excited state from E2. So, in density matrix notation, we started in state A, and then we made a transition to NA, and then E2 came in, and we made transition to BA. And now, essentially, we changed the ket side, and now we need to change the bra side. So the real parts interacted here. Now the imaginary parts interact. So the imaginary part of E1 interacts, and the imaginary part of E2 interacts. So this stays B, this goes to N, and then lastly, this N changes to a B. Okay. So that's essentially the process, and there's real and imaginary parts because you can write the cosine in terms of complex exponentials. And here I said the difference between your frequencies has to be your vibrational frequency of interest. Now what if you don't know your vibrational frequencies of interest and you're just trying to get a Raman spectrum? Well, you could do spontaneous Raman, but you want to do stimulated Raman because stimulated Raman gives a whole heck of a lot better signal to noise. And notice that the difference between stimulated and spontaneous Raman is in stimulated Raman, you provide the E2 field, whereas in spontaneous Raman, the vacuum provides the E2 field. And since the vacuum is only producing the E field I don't know. There's not a very great probability of the vacuum producing that, but if you make it already there, well then there's a great probability of that Raman transition happening, and that's sort of a hand-wavy reason of why stimulated Raman gives you way better signal than spontaneous. But if you don't know your vibrational frequencies, well then your E2 could be a broadband pulse. So what I like to look at is a figure like this. And so this is the stimulated Raman spectra, stimulated Raman scattering paper I showed in another video. And this is figure 5 here. So there's narrow band, and that's when you know your vibrational frequencies, you just want to monitor them. So the pump is the same thing we've been talking about here. It's the one that's greater in energy if you're doing Stokes scattering. And then your tunable Stokes is just your what we were calling E2 here. And this is when you know your vibrational frequency, where exactly it lies. If you don't know where exactly it lies, well then you can make a broadband probe. And essentially you'll have, there's a lot of different frequencies between the pump, and there's a difference between here and here, and then here and here, and here and here. And all those will give you stimulated gain or stimulated loss. So initially your broadband pulse might look like that, but then afterwards, since you're going to get stimulated Raman gain on top, it's going to look like this. And what you do is subtract the initial pulse from the detected pulse, and so you subtract them, and what you get is your Raman spectrum, where this is your frequency axis. So that's a little bit about how the stimulated Raman experiment's done. Thanks for watching, and have a great day.